So we have another example we're going to take a look at. So the model y equals ax to the n, so this would be a power model, was fitted to the data below. Using nonlinear regression, it was found that a was approximately 6.894 and n was approximately 1.359. So the first part of this example was to draw a scatter diagram of the data and sketch the fitted model on the same set of axes. So once again, the points in blue are the points from the table up here. And then this is the equation. So once again, you can put that equation in the y equals in your calculator and then press second graph to get a table of values. So then once you have your table of values, you can use those to be able to plot and connect that black curve. So once again, we're going to calculate the residual of each point. So I put my calculator screenshots in here. So you should follow along to make sure that you get the same things. So in my first one, my first picture up here, I have my L1 and my L2 filled in. I have the equation that's going into L3, and then I pressed enter and it filled in these values in L3 for me. From there, I said, okay, well now I want L4 to be L2 minus L3. So then I hit enter and it filled in this column of data. So if you were asked to calculate the residual of each point, this table on the right-hand side is what you would write down on your paper, okay? You would say, okay, these were my x's, these were my y's, and these are my residuals. And if you look, you just copy them right out of the calculator, rounding to 3 sig figs. And then hence, calculate the sum of the squared residuals. So I just use, remember we can do the stat calc one variable stat on L4, and then we're looking for sum of x squared, and that will give us this number here. And once again, it's rounded to 3 sig figs. Now, part D is a blast from the past, okay? So we want to use the natural log of x and the natural log of y to fit the power model to the data. How does this model compare to the one above? So we did this way back in Unit 5. So you may want to look over those Unit 5 notes a little bit, but I have everything here also, but it may not be a bad idea if you need a little bit more to go back to Unit 5. So in my calculator, in L1, I have my x values. In L2, I have my y values. Now, they wanted us to do the natural log of x. So my L3, I put in ln of L1, which would be ln of the x values. In L4, it's ln of L2, which means I'm really doing the natural log of the y values. Now from here, we tell our calculator to do a linear regression using L3 and L4, okay, which is what I have here. Now from here, okay, if you look at the calculator, we have our A and our B values. So we take those and we put them into the linear regression equation. So remember though, we didn't actually use x and y. We really used the ln of y and the ln of x. So when we substitute these in, it's ln of y instead of regular y. A to 3 sig figs is 1.03. ln of x, because we're using the natural log of x, not x itself, and then plus the b value, which is 2.52. As I wrote that down backwards, 2.52. Okay, so now as I continue on, I'll have the ln of y equals 1.03 ln of x plus 2.52 ln of e. So this is the step that we need to remember, is that in order to condense logarithms, both pieces here that are being added together have to have a log. So ln of e is equal to 1. So therefore, we can substitute that in, and it's not going to change the value, but now both pieces have a natural log, so we can condense. In the next step, what I did was I rewrote my coefficients as exponents. So I still have ln of y, and the 1.03 became an exponent, and the 2.52 became an exponent. Now, because I'm adding, what I can do is I can actually multiply the bases together. So I have ln of x to the 1.03 times e to the 2.52. Now, since I have just one ln on both sides, I can cancel those out. So that leaves me with y equals e to the 2.52, and I just move that to the front, and then times x to the 1.03. So if I do e to the 2.52, it gives me it gives me the same number, 12.4. Okay, so I have 12.4 times x to the 1.03. So we now have our model. Okay, so there was a review from Unit 5. So once again, just remember, we use the calculator to find the linear regression using the natural log of x and the natural log of y. From there, we simplified using the laws of logarithms, and then we ended up with a power model. How does this model compare to the one above? So that's the next part of the question. So now we're looking to compare the model they gave us with this model that we just found. So the model they gave us was y equals 6.894 times x to the 1.359. So if we look, the power of x for the power model found right here is 1.03, and that's pretty close to the 1.359. But then if we look at the A value, here we had 12.4. The other one is 6.894. So those are really far apart. From here, I would like you to pause the video and go through the process of finding the sum of the squared residuals for this model that we just found. If you need to, you can go back and look at the calculator steps, but I would like you to pause the video and find the sum of the squared residuals and then come back. At this point, you should have found from your model that the sum of your residuals, sum of the squared residuals, rounded to 3 sig figs is 1,160. So this model is less appropriate since it's larger than the 122 that we got for the original model. So that's how these numbers can help us, because if we have two models that we're trying to choose from, we can choose the better one by choosing the smaller of the two sums of the squared residuals. So in this case, the exponent was pretty close, the A values were really different, and when we looked at the sum of the squared residuals for the power model, it was way different than the one that we were given.